Hello, everyone. So my name is Ofri Telem, and I'm a postdoc at Berkeley/LBL. And today I'll tell you about the fact that axion strings are superconducting. And it's a funny story. The reason we chose this title is because this is kind of like Schrodinger's fact. Half the people would say that it's trivial and they knew it already, and half the people are completely shocked by it. And in any case, it wasn't completely clear to us what the cosmological implications of that fact are. So we set on to discover. So since the talk is going to be very brief, I'm going to kind of divide it into three take-home messages. The take-home message number one is that axion strings are superconducting and that their evolution in the early universe is affected. So it affects, usually we think of axion strings in the early universe as going through scaling, in which string length enters the horizon, but string length is also lost through reconnections into loops that then radiate axions and decay. And this delicate balance is somewhat violated by the fact that axion strings are superconducting and generically incur currents on them, electromagnetic currents on them. So it's been known for a long time, since '81, that axion strings have chiral massless fermion zero modes. And that can easily be seen by solving the Dirac equation for fermions that have a Yukawa coupling to the scalar that is associated with the axion string, the winds around the axion string. For example, if we think about the case VZ scenario, in this case, we took a bottom type vector like quark to be the heavy case VZ fermion. It has a Yukawa coupling to the scalar that the PQ scalar that winds around the string. And if you solve the Dirac equation, which we did, and people did many, many years ago, you find that there's a chiral zero mode on the string. And you can see this illustration that the wave function of this chiral zero mode in the transverse direction to the string kind of extends to roughly the inverse FA, as the VEV of the scalar grows from 0 to FA in the bulk. So that's been known. And there's also an index theorem which proves that this is the case. Now the question is what that does. So these zero modes, they're massless, and they move with the speed of light along the string. Now, specifically in this case, VZ scenario, and also any scenario we could think about that has a number of domain walls 1, there's also an electromagnetic anomaly. So the charge carriers on the string couple to electromagnetism as well. If you look at it from the point of view of the worldsheet theory, it looks like there's a gauge anomaly on the string. And so charge just appears out of nowhere. And this is, of course, a paradox, which was solved in '84 through the notion of anomaly inflow, which is well known from the more formal sides of theory. What really happens is that there's a quantum generated Goldstone-Wiltshire current that's created in the bulk. This is the term at the bottom here. It just emerges when you calculate a loop in the presence of the theta FF dual term. And what happens is that this is a radial current that flows into the string and feeds the charge on the string. So even though from the worldsheet theory of the string, it looks like charge is born, it's actually flowing radially. And this is kind of similar to the quantum Hall effect, even though there the difference in dimensions between the edge and the bulk is 1, while here it's 2 between the 2-dimensional kind of theory and the string and the 4-dimensional bulk. So this has been known before, but we're considering the pheno implication of that. So one immediate implication of anomaly inflow is that the strings are actually superconducting. So if, because of this Goldstone-Wiltshire current, if we have a background electric field, that just feeds the current, and the current doesn't dissipate. And this equation, which was first written down for the strings by Witten, but for non-anomalous strings, but also by Callan and Harvey from anomaly inflow, is exactly the London equation for superconductivity. So axiom strings are superconducting. Now, as the strings move in the early universe, they can, if they move through a magnetic field, you can just boost to the rest frame of the string, and the magnetic field translates into an electric field that's applied along the string and creates a current along it. Now, just naively from equipartition, we would say that there's an induced current of the string which goes like the temperature. But also what we will see in the last part of this short talk is that if there's a primordial magnetic field, or PMF, that's generated in the early universe from inflation or from a first order phase transition, that could induce huge currents, 10 to the 15 amps and even more than that on the strings. And that surely back reacts on the string evolution as well, and also the axiom density. So the equation that covers current evolution has three terms. There's just the superconductivity term, in which the induced current, the current grows as a result of the magnetic field. But there's also a drainage from, can you hear me, by the way? Good. So there's also a drainage from redshift, and also from particle physics, which provides leakage processes. So let's see how these leakage processes work. Generically, if you have a case VZ fermion, in order for it to decay and not be a stable relic in the early universe, it has to have some Yukawa, whose value we don't know, that allows it to decay to standard model quarks. Now, this term could lead to current leakage from the string. For example, through a plasma particle that's incident on the zero mode on the string, it hits the string and just annihilates it through a Higgs and eventually emits a gluon. So this is how a plasma particle just hits the string and it just kills one of the charges on the string. And we calculated the rate for that process. And the important thing here is the plasma particle, this is just some particle in the bulk that's incident on the string, has to hit the string. And the string is very small. Its cross section is 1 over F8 squared. So this is a suppressed process, which also decouples at low temperatures. The other thing that could happen is there could be a fluctuation of the string, which is quantified by a Nambu-Goto boson that is associated with the position of the string. And that could travel and just knock off a zero mode off of the string. But that's suppressed by F8 to the fourth, one time because of the coupling of this fluctuation to the zero mode, and the second time because we need an off-shell case VZ fermion whose typical mass is F8. So here, this is also suppressed by F8 to the fourth. But note that there's always a prefactor here of the Yukawa squared, which is unspecified in a Mondale independent thinking. So how does this influence the evolution of strings? So if strings have huge currents on them, what happens is it creates an azimuthal magnetic field around them, which shocks the plasma that the string goes through. And you can go through the calculation and see that it's effectively a cylinder, a magnetocylinder that's traveling through the plasma and incurring a friction on it. And the radius of this effective magnetic cylinder goes like the current. So that gives an effective dissipation on the string. So that's the way it feedbacks on the evolution of the strings. It creates a drag force, which sharply decreases the average string velocity in the universe, because the loop chopping is proportional to the velocity, or velocity dependent. If the velocity is very low, there are no reconnections. And so loop chopping is suppressed. More string length comes into the Hubble horizon, and you get more strings per Hubble. So that's the first take-home message. Second take-home message, let's see how I'm doing, is that vortons, which are stable loops of charged strings that are stabilized by their mutual repulsion because they're charged, are inevitably created from axion strings. This is not a model dependent statement. These vortons happen at the temperature where the leakage decoupled, so their charge on these vortons is conserved, and we can estimate their abundance. And you see here that their abundance with respect to the overall dark matter abundance is very dependent on the temperature where the leakage decouples, which in turn it depends on the strength of this Yukawa. So depending on whether this leakage is strong or weak, you could either have a scenario where the whole thing is excluded because vortons overclose the universe, or if the Yukawa is order 1 or 0.1, then there's no problem because the vortons are not abundant because there's a lot of leakage and not a lot of them are created. The third take-home message is maybe a little less model independent, but we still think it's very interesting. The thing is, if you have Axion strings embedded in some primordial magnetic field, whatever the source will be from inflation or from a first order phase transition, you get a huge current. You got many, many more strings, like 10 to the 4 more strings than the scaling value of 1 string per Hubble. And sometimes you also get many more axions in this scenario. So just a one slider, there's a lower bound on the intergalactic magnetic field today of 10 to the minus 13 Gauss, if you take into account that it has to be space filling, and that's from a non-observation of secondary gamma rays from TV blazars. It's compelled to consider a primordial source for it, and there are many excellent reviews that detail how the magnetic field coupled to the plasma redshifts in the early universe, and it's parameterized by this parameter alpha that's linked to the spectral index. And we just show our results for 3 values of this alpha corresponding to a primordial magnetic field from 2 scenarios of phase transition and 1 scenario from inflation, which is actually in the backup. So what do? We don't have a full scale simulation. We use the known analytic model, the velocity-dependent 1-scale model by Martins and Shellard, but we couple to it a friction term, which one can show, and this was shown also by Dimopoulos and Davis in the late 90s, that the friction due to the current is of this form. So we couple it to a current growth equation, and you can see color-coded here what the different terms mean. L here is a 1 scale that corresponds to the interstring distance, the curvature radius, and also the correlation length. And we just solve the differential equation in the presence of a primordial magnetic field from inflation and from first order phase transitions and see what happens. So the first thing that happens if there's a phase transition, let's say we started almost at scaling, and we just turn on a magnetic field. It immediately charges, as you can see, 10 to the 15 amps on the string. And that immediately slows down the velocity because of the drag force to almost 10 to the minus 5. And that stops reconnections. So after this transient, for the rest of the evolution, let's say we turn it on at 1,000 GeV, what happens is the velocity goes immediately down, starts accelerating back up, but not enough to reach the scaling solution again. So what happens is a renewed stretching phase in which there are no reconnections, more string goes into the Hubble volume, and this number is the number of strings per Hubble compared to the scaling value of order 1, or maybe if there's scaling violation up to 15, we get here more than 10 to the 4, between 10 to the 4 and 10 to the 5, and almost 10 to the 6 in the other scenario, just because of this renewed stretching. So that's the huge effect. Now we can map the parameter space with the temperature in which the magnetic field appeared and the strength of the magnetic field today. And we can have contour lines of the enhancement in the number of strings per Hubble at 1 GeV when we care, when the axions are produced, the axion dark matter is produced. And you can see this huge enhancement. What we also care about is what happens if you scan over FA, because that's linked to the bounds on axions. And if we fix the magnetic field today to the lower bound, the experimental lower bound, and we look at the resulting axion density, now the contours are the axion density, we see that there are chunks of the parameter space that are just ruled out for every FA. So for example, here. So that's the big effect. And we estimate the Axiom density using an estimate from Villador et al. And we can discuss in the discussion the validity of this estimate to our scenario. Lastly, I just took a slice of this 2D plot. And you can see that, for example, here we get too many axions. So this scenario, when the magnetic field starts at 1,000 GeV, is completely excluded for every value of FA. And it's really independent of like the exact UV model. It's for every magnetic field. So that's the power of these results. They're rather model independent. To conclude, Axiom strings are superconducting because of anomaly inflow. Thermally generated current stabilizes loops with Axiom strings. They're vortons. They could overclose the universe unless the leakage is strong, and that depends on the Yukawa that connects them to the standard model. And this is inevitable and model independent, for Axiom strings. If there's any kind of primordial magnetic field that's responsible for the intergalactic magnetic field today, the strings incur 10 to the 15 amp currents and even more. That creates a new dominant friction on them, which enhances the number of strings per Hubble by 10 to the 4 to 10 to the 6 orders of magnitude. And in some of the parameter space, that creates so many axions that the scenario is just ruled out for all values of FA. That's it. Thank you.